Okay, so we're going to talk about data mining. Okay, this course is about data mining, right? But I'm sure you have heard about the word data science, okay? So how many of you have not heard of this word? Anyone? It should be something familiar to everyone, right? Because it's like some kind of hot topic nowadays. So now data mining is actually something that is very closely related to data science. In the old days, before this word was coined, like data science, right? Basically, a lot of things that when people actually do data science, they are actually basically doing data mining, right? So I guess data science, the word is actually more classy, right? So then it got hold of, it got attention from the masses. But basically, what you are doing in this course is doing a lot of data science. Okay, it's just another word. It's just using another name for it. Now, when you use the word data science, right? A lot of people focus on the first word, data. I have a different opinion. I focus more on the science. Okay, because without the science, your data has no value, right? There's actually a misconception that the more data that you have, the more information you have. This is actually not exactly true, because the so-called data that you have may actually be just rubbish, right? And they may not be able to support any sort of claim that you wish to make, unless you have actually done very sound, you have a very sound science behind the data. So I want to first talk about the science, right? So if you have had some background training in science, maybe you appreciate this better, right? Okay, so if you have gone through the notes there, I'll just quickly elaborate on example 2.0.1. So this is an example of an experimental design, right? Which is simple enough. It illustrates the kind of data that's generated from very sound science. Okay, so basically, like for example, you have some bottles here. Okay, where you can actually grow some vegetables. Okay, so you could have, let's say, 5 or more. Okay, right? So you fill this bottles with some solution, okay, and you do the same for these bottles, okay. And you also fill these bottles with the same solution, right? Okay, so your aim here is to study the effect of magnesium, right? Magnesium on growth of the vegetable, okay? So of course, this would mean that you maybe you add, this is maybe very low in magnesium, and this is maybe high in magnesium. All right, so you have a difference in what we call the treatment. Now the solution in this experiment, all right. Okay, here I give the example of A, B, C, right? So there may be another set here. So you also have the same amount of solution. And this may be very highly elevated amounts of magnesium, right? So now you have, you want to do this experiment. You want to study the effect of magnesium, these 3 levels of magnesium on the growth of the vegetable. So the, the vegetable may actually grow, depending on the particular species, right? It may actually grow better with low levels of magnesium, or it may actually grow worse with lower amounts of magnesium. So it's actually particular to maybe a particular type of vegetable. So now you have the this vegetable. Okay, so now you have some kind of saplings, right? So you have a lot of these saplings where you got it from nursery. And then what you do is you kind of like allocate them into these bottles, right? Okay. The first question that I want to ask you here is this. How should the allocation be done? Anybody wants to give a suggestion? Okay, a lot of you use the word random, right? What does that mean?
To prevent any bias that is happening. That's why we use random.
Okay, so so when you assign randomly, that means you might have some mechanism like this. So this may be, you may actually label it as 1, 2, 3, 4, 5. This may be 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? Okay. So you would then actually you could actually have some mechanism that's like this. So you have a plant from here, right? Okay. So it might actually go to any of these containers, right? So what happens is that you have 1 to 15, right? You have 1 to 15, the numbers here. You randomly pick one number from here, following a uniform distribution. That means each of these numbers has equal chance of being picked, right? The simplest way to do this may be, I mean, of course, you're going to use a computer to do it, right? There's a function to simulate random numbers. But then, of course, if you've studied some computationally intensive methods in statistics, then you realize that that actually there's an algorithm to simulate uniform random variables, okay? But then just intuitively, you can also do that using a mechanical means, right? You just have 15 pieces of paper, small pieces of paper. You just write the numbers 1 to 15, right, on each paper. You then put the papers into a bag and then you jumble them out and then pick a number, right? Okay, so basically if it gets number 2, then you would assign it to this bottle, okay? And then so on and so forth, all right? So the purpose of this, this way of allocation is to avoid any kinds of potential biases, right? For example, your this plants, right, that come from the nursery, some of them they might actually have a different. Some of them might be slightly older, and some of them might be slightly younger, right? So if you allocate all the older ones to some particular treatment here, then you will have some what we call confounding, right? Because after that, you don't know whether the effect is caused by the magnesium or it's just simply caused by the fact that the sapling is actually older. Okay, so we want to avoid this kind of confounding effects. So what we use a randomized optimization to break the confounding, right? Okay, so then after we randomly allocate, right? So we have the plants sitting nicely here with the roots, okay, and so on, right? So plants are sitting here. So one more thing here is that, of course, you must ensure that the amount of the solution, right? The volume must be the same, right? So you put the saplings here, right? And then after that, you will wait for a certain time, and then you will for them to grow, and then you will harvest them and make observations, right? So during the growing period, you have to make sure that all of them receive the same amount of light, right? Okay, because otherwise otherwise your lighting will enter as a confounder. Like for example, if this particular treatment, right, receive a lot of lighting, okay, and this one receive a very little lighting, okay, then at the end when you observe the difference in these three treatments, right, you cannot be sure that it is actually caused by the magnesium. It could actually be explained by the light as well. Okay, does that make sense to everyone?
Yes.
So you have to be very careful about giving explanations. In order that there's only one possible explanation for the variation in response that you see, you got to control the other variables. That means the other variables, they cannot vary at the same time. Otherwise, you are not sure. Okay? Otherwise, at best, you can just say you are not sure. All right. So with this kind of experiment, you can actually control it very well. Yeah. And after that, after a certain number of time, you can actually then harvest them and then measure whatever things that you think are important. Like for example, here you might actually want to measure its mass, right? Maybe the length. Okay, the length maybe like from the root until the height of the tip. And then there are many other possibilities, right? You may actually also want to measure. This will be what we call quantitative. These are actually quantitative, right? Because you can actually use some kind of device to attach it, to assign a number to this. Or you could also record categorical response variables. Like for example, you may actually just try to observe whether there's some kind of yellow spotting, right? Yellow spotting usually indicates some kind of problem with the health of a plant, okay? And things like similar things that are meaningful at the subject matter point of view, okay? So once you have done this, right? Because you have controlled the other possible sources of variation properly, then suppose, for example, if you use height as the response variable, for example, let's say here if the mean is let's say 10 cm. Well, okay. Maybe this one the mean is 15 cm, and this one the mean is 5 cm, right? So of course then you will see that on average they are all different, right? 15, 10, 5. But this is not enough. One of the reasons why we have different these are what we call replicates, right? So the replicate is the purpose of the replicate is to study variation within treatment. Because for any treatment, there is bound to be some variation. And you want to see whether this variation is large or small, okay? So if they are more or less consistent, right? So the variation will be small. Otherwise, the variation will be large, all right? So therefore, usually when we report this, we don't simply just compare the mean, right? But we also would like to know something about the amount of variation. So in terms of the standard deviation, all right? So there might be, the standard deviation might be about the same, roughly. In this case, then it is very clear that the magnesium affects the height of the plant substantially, right? And this effect cannot be explained by chance, because if you look at this, so roughly this will be, you have, if you roughly sketch it, this is like 5 is on a scale of 5, it's 5. So the other one is 10. So it's going like this, and the other one is 15, right? So if you look at the distribution of the height, okay, plus minus 1 centimeter, 1 cm, right? So you'll find that they kind of like more or less form some kind of distinct groups, right? So that also kind of like convinces you that the variation in height is actually mostly due to variation of treatment, okay, in the magnesium concentration. So the conclusion is actually very clear, right? That there are no other possibilities that can be admitted, because you have already made the other, you have already controlled for all the other possible sources of variation. Of course, it is not possible to control like 100% everything, right? But that doesn't really bother us, because as long as you control the main sources of variation, that should be enough already. Okay. So like what those sources of variation are will depend on context, right? Like in this case, for plants, obviously light is important, okay? And maybe perhaps also humidity, okay? That's why you have to grow them under the same condition, right? And that takes care of the confounding, right? You are actually avoiding confounding, okay? So is this example clear?
Yes.
So this is actually a basic way to think about science, right? If you are able to intervene in an experiment and you want to study the effect of some particular treatment, then this is something that you can do. Okay, and this is a very powerful way to understand nature. All right. Now, of course, this is very nice, right? But most of the there's another type of data in the real world where you cannot actually have any intervention. They are just basically data that comes from natural processes. At most, you can actually observe them. And does that mean that you cannot actually study them, right? Just because they don't have randomization, okay? It turns out that we can still study them, right? But with some kind of, when you study this kind of observational data, then we have to be very aware of the issue of bias, right? You cannot just pretend that it doesn't happen. And I mentioned this because in data mining, this issue of bias is actually ever present, because in data mining, most of the time you're going to work with observational data. That means data that's collected without any particular experimental design. And under this situation, a lot of other possible factors can explain the variation in the response, okay, other than the variable that you're interested in. So be very careful, okay? It's not as straightforward as the situation in experimental design. So I gave you an example, 2.0.2. So this is an example from sociology, right? So basically, you have a situation where the interest is in comparing income disparity between men and women. So what she did was that she just used the tax records, right? So this is the tax records. Okay. So you have the tax records, right? and you have one part is male, the other part is female, for example. And then after you get the tax records, you can actually plot a distribution, right? So you can have the distribution of income for men. So maybe it looks like this. And when you plot it for the female, it also maybe looks something similar. Okay. Of course, they can calculate some characteristics of the distribution and maybe try to compare the two distributions using some statistical tests, right? And they find that, okay, so these two, like for example, they might actually use maybe the Kolmogorov, the KS test, the Kolmogorov Smirnov test, right? So this is to test for whether two distributions are the same. Okay, so the researcher can do something like this and come up with some p-value that is maybe like 0.5, which is high, right? High meaning that they are not significantly different. Basically saying that the two distributions are the same. There's no reason to suppose that they are different, right? Any difference is just explained by chance. Now, what do you think about this approach? So basically, this is what this sociologist did. She got the tax records. She extracted those for the male and the female. She looked at the distribution of the income. This is the income. This is maybe the relative frequency, right? Same here. And then she has learned some statistics, so she tries to apply it. And she's very happy that there's no significant difference between these two distributions, right? And then she makes the claim that income disparity has disappeared. Okay. So anyone wants to challenge, how would you challenge her view? You challenge her analysis.
Not everybody reported their income, so the data is not complete.
Okay, so very good idea here. First thing is the tax record is incomplete, right? In fact,
Identity for all the population that gets income.
Okay, so some people never report. And when they don't report, it could be because of what? Too low, right? Usually you are only required to report to the revenue department if your income exceeds certain threshold, right? So if you don't have to report. And some people, they just try to, these are the dodgers, right? They purposely don't want to report so that they cannot be taxed. Okay. Okay, so this is, so if it's incomplete, how would that affect this graph? Suppose you can observe suppose you are able to observe the incomplete data. Suppose like, just suppose, right? Give a scenario where the two distributions will be different.
It will be actually more having a heavy tail on the left side. Is it not heavy tail? I mean, having a higher distribution, so this distribution will actually skew to the right. If I'm not mistaken, I forget the right and left part. Sorry.
Oh, skew to the right means the tail is tending towards the right. Skew to the left means the tail is tending to the left.
Yeah, so it should be skewed to the right. Yes.
Okay. So I think one situation is it could be that this part here is missing, right? For the guys, or maybe these are the men, right? These are the women. So maybe the guys, they have a whole bunch of dodgers here. They just don't report. They earn a lot of money because they are close to maybe politicians, and they are not afraid of dodging taxes because people will protect them. So then you cannot see these people, right? Because you're using tax records and they're absent. You can't actually catch this. And so the reality may be something like this rather than this, okay? And the other possibility may be that perhaps a lot of the women, right, they're earning very little. So in fact, if you actually can see them, they're actually here, okay? So once you have a lot of these females here, then the graph may be something like this, okay? So then when you compare with this graph of the male, even without the dodges here, they are definitely different, right? Okay, so the first issue here is the incompleteness of the tax record. Okay, so are there other comments?
Maybe we can actually drill down to it, like looking at the age, work categories, and areas to see whether is it actually like for every particular groups, like maybe age groups 20 to 25, is it male and female is the same, and then so on for the age part. And work category wise, it will be like maybe different ranking actually they have some bias over there that we doesn't know.
Okay, great. So age is also here. So age is actually, so just now the tax record can be biased because there are people who never report and they are dodgers. They're either too low and they're also dodgers. The other issue here when you directly compare the income here is the age distribution may be different, right? May be different between the male and female. So generally, people who are either too young or too old may actually earn not that much, all right? Because they are not at the prime of their age. So without knowing anything about the age distribution, right, it may be confounded by age, so we don't know, right? So one possibility may be to actually obtain more refined kind of data. Okay, that means perhaps you are studying this with respect to different age groups, right? So for example, you might actually want to study like, okay, maybe this is the male distribution, this is the female, this is like maybe age group from maybe let's say 15 to 25. Then you look at another one, maybe this is 26 to 40. Okay, so the curve might look somewhat different, right? So you look at different, maybe this until 50 and so on, okay? So you look at different age groups to account for the age effect. For certain age groups, the income distribution may be the same, maybe like not significantly different, but for the others, they might be. Okay, so if you consider age group, then you see that why you want to do this kind of analysis is because the phenomenon that you see here, right, is actually affected by a lot of different factors. And therefore, you should not be very so naive that it's actually just determined by one factor, which is the gender of the person, okay? So you have to, so in this case, you basically, you have to consider something about what you know about the domain knowledge. Well, in this case, maybe some social aspects, right? Okay. What else? What are the other possibilities? So age here acts as a confounder, right? So we have to study, we have to try to be aware of this factor, and then maybe perhaps control for this confounder. What else can you control?
Someone mentioned that it can be influenced by location as well. I mean, Ziyun actually mentioned that in the chat. Yeah.
Okay. Oh, let me look at the chat. Okay. So yeah, sure. Place where people stay, right? So maybe it's the urban and rural divide. All right. So this could be one of the confounders. But okay, so any other suggestions? Right. Okay. Education background. That's good. Education level is known to be very strongly correlated with income. Okay. So actually, that is actually a no-brainer because if you don't receive much education, usually a lot of opportunities are closed to you. So you're not able to access certain jobs that require certain levels of knowledge. Okay, so of course that would automatically limit your income, right? So yes, so definitely. So if the education level of women and men are different, right? So perhaps there's a bias in society where there's boys are more favored to go to schools. Like in a lot of old societies, that's the thing that happened, right? They would rather send the boy to school rather than the girl, okay, because of some kind of tradition that emphasizes the male genealogy, right? So that would create a differential in education between the two genders, and is the education that actually explains the difference in income more than actually the male or female. Okay, so this is actually very powerful, right? Education. In fact, education is also very strongly correlated with the fertility of a woman. So the higher the education, the lower the fertility. Okay, fertility in this case means that the number of the average number of children that is given by a woman. The more highly educated a woman is, the less children this woman will bear. So it is inevitable that any society that becomes highly industrialized, the birth rate will drop. This is for certain. Okay. So therefore, if you're a government person and you want to control the birth rate, right? Let's say, for example, in certain countries, the birth rate is too high and you have overpopulation. The best way to control it is actually to give to actually give the girls more education, right? So that's one way to do it if you understand these relationships. Okay. Anyone else want to suggest some other potential confounders? So this is also a confounder in this study. Race. Okay, so race is actually known to be associated with differential in income, and it's a very complex variable here because this race is actually tied up with a lot of things. It's tied up with history, culture, and tradition, and these are very complex processes. For example, historically, culturally, some groups of people may have been working in certain profession for a long time, and they pass this knowledge among them from generation to generation. So because of that, right, they tend to have some kind of a head start in certain professions. And therefore, if that profession pays well, then they usually will earn better. Compared to, let's say, like, for example, certain culture and history, historically, maybe certain groups, they live in forested areas and they rely on hunting and all that. So they will be very good at this kind of things, but in terms of you're talking about a modern economy, then they will do very badly. Okay? And then it's got nothing to do whether they are men or women. And of course, and you can't actually attribute it to their race because race is a very complex factor that incorporates different many different processes. Right? Okay, so it's complicated enough already, right? That now you can see that when you have observational data, although you can actually do analysis and try to look at distributions and things like that, when you think about the interpretation of the results, you have to be very, very careful and be aware. It's not that you can't analyze it, you can, but a lot of your statements will have to be very much qualified. You can't make a very general statement. You can say that, yes, like for example, in this case, let's say your p-value is more than, let's say 0.2. So in this case, you could say that, yes, with respect to this age group, right, for the younger age group, the male and female don't earn, the difference in their income distribution is not significant. But in other age groups, maybe perhaps the p-value is actually very small. So there's a differential in income. So then you have to kind of like qualify your statements, okay? So this example is just to give you some idea that when you try to do analysis of data that comes from observational study, you have to, you cannot be too naive, right? You have to think about the problem in a more thorough way, okay? All right, okay. Are you able to understand this point?
Yes.
So I make the distinction between what you can do in an experimental study and what you should actually consider when you are dealing with an observational study. Okay. Right. Okay. So then I give another example about how to approach observational study using the example of the cholera outbreak. Right. So this is a very interesting study, and it shows the power of making careful observations. And this study actually is one of the early example of, I would say it's actually an early example of data science. In data science, nowadays people tend to think that you need a lot of data, like large data, big data, things like that. Actually, no. As long as you have sufficient amounts of data and there's a science to it, you can call that data science. Okay. And in fact, this would be a prime example of doing data science, because this person, right, this John Snow, he is not just content with looking at direct associations. Like for example, he's actually sharp to notice that the disease cluster happens around water pumps. So then he hypothesized that the water pump, the source actually comes from water. And then, of course, his critics will quickly point out that, but other pumps don't have, right? If you claim that it's coming from the water, how come the other pumps don't have? And this is actually a valid objection. And it turns out that it's because the source of the water for the pumps are actually confounded with the supplier. And because he understood that, he went to check the suppliers of the pumps. Right? During those times, the water pumps, they're not like now. Now you just turn on a tap, everything comes, right? During those times, they actually have contractors who actually go and get water from the river, and then they supply the pumps. And then you usually pay a small fee to be able to use the pumps, right, to get water. So then he because he has this thinking, he finally discovered that yes, he could actually explain why his pump has disease clusters, but the other pumps don't have disease clusters. It's because of the different companies, and they take the water from different parts of the river. One is the upstream, one is the downstream. And we all know that the downstream water material is actually polluted, right? Because people's, you go to the toilet and all the things will get flushed, and it just go to the downstream. Okay, whereas upstream, the water is usually cleaner. Okay, so then that was very important because I mean, like, it's common knowledge that everybody boils water before they drink, right? Otherwise, you might actually get sick. Actually, this practice is actually a public health advice that is derived from this incident. It's just that you don't know it. All right, because a lot of places in this world are colonized by Great Britain, right? So because of this example, they actually, when they got this knowledge, when they went to their colonized places, they actually spread this advice. They institute it as a public health requirement. So then it became just common knowledge, and people forget how you actually got these rules, right? It didn't drop from the sky. Okay, this kind of simple knowledge actually the works of people putting their minds to a problem. Okay, so it's very fascinating to me, at least, because this kind of simple rule actually could help save many lives, right? Think about it. If the advice is boil the water before you drink it, will save you from waterborne diseases. This is actually not immediately apparent because in the old days, right, maybe just 200 years ago, people in Europe actually they just literally just drink water, If they get the water, they just drink it. It never occurs to them to boil it. And the reason is very simple. If you don't know that there are things living, there are small things like bacteria living in the water, why would you bother boiling it? Right? You would think that it's perfectly okay to just drink it because you wouldn't suspect that there's anything there. Right? The tradition of boiling water tends to be more in East Asia because of the habit of drinking tea. So people tend to boil their water one shot, right? So that's why during that time, this kind of cholera was more common in Europe compared to Asia. Okay. All right. So I hope those examples give you some flavor of how we should approach the problem of thinking about data. Yeah. Okay. So are there any questions that you would like to ask regarding these examples?
No question.
If you are interested about the John Snow, there's actually a very famous map called the John Snow map. You can just Google John Snow's map, and you will see the map that he actually used to kind of like find out the cluster of cases around the water pump. It's a very classic example. Okay. All right. Okay. So if there are no questions, I'll just quickly move into what we mean by data, right? Okay, so maybe before we actually go to chapter 3 about data, maybe you can tell me something about what you understand when you hear the word data.
Some information that is collected.
Okay. Anyone else want to say something? What comes to your mind when you hear the word data? Observation.
There's variables.
How about others? Spreadsheet. Okay. Could be qualitative or quantitative. This is more like a characteristic. Collection of records.
Maybe collected from some kind of experiment.
Maybe information from experiments. Pattern. Investigation. Some statistics collected for analysis and reference. Right, okay. So we have like a whole, so I just wanted to the purpose I asked you this question is to illustrate the diversity of mental pictures that people have when they hear a simple word like this, data, right? And of course, this is like, so it's actually something that is very multidimensional. There are many different aspects of data. So usually parts of it, so different people actually capture maybe certain parts of it, all right? So data, of course, so you have all these things like some information that's collected, okay? So if it's collected, then it's data. If you don't collect it, there's no data, all right? So you only have data when you actually do collection, right? Otherwise, we are not aware of it, right? So that's one thing. Observation, definitely, if you don't make observations, you will not have data. Patterns are found in data, and this is what this course is about, data mining. We want to find patterns from the data because these patterns are potentially useful as new forms of knowledge, okay? Variables, yes, they are related to variables because when we study variables, right, different variables, like for example, you can think of our weight is a variable, and you can collect data on weights, and you can actually collect data on heights, all right? So they definitely, the variables, when you measure them, you collect information about them, you get data. And of course, investigation data comes from any investigation. Even written reports is data, yeah? A lot of times people might not associate written reports, text documents as data. These are actually data because you could actually do analysis of word frequencies in documents. And that's actually a kind of analysis. And a kind of, there might be some patterns of word usage in those documents that will inform you of some interesting things. So, so even newspapers is data. All right, but usually people don't think about that. They just think that it's just something for reading. It's data in a very simple sense. Have you seen, maybe have you seen something about word clouds?
Yes.
The word cloud is basically some kind of graphic whereby words that have a
Higher frequency.
will be large, will be represented like in a larger font. Those that have a smaller frequency will be represented as a smaller font. So that will basically tell you, like, if you have a lot of documents, if you do a simple frequency count, you could actually know something about the main topic of those documents without actually reading them, right? Because the major words, the keywords that come out, they will tell you something about what these documents are related to. Okay, so that's actually also data. So you can see that it's everywhere, right? It's all around us. And yes, spreadsheets, right? Once you have data, you want to store the data, right? This is more about storage, isn't it? You have data, you must store it, otherwise it's lost. And of course, you could store it by simply writing data on a piece of paper. You will quickly abandon that approach because you know that it doesn't scale, right? Like for example, if you're gonna have like thousands and thousands of samples and you write it on pieces of paper, that might be too much, and you might actually lose the paper. Okay, so people just record it in spreadsheets like Excel sheets. Okay, that's for storage. And of course, so some of you might have heard of databases. Yeah, so modern data are usually stored in databases whereby the data is actually structured. They are organized into particular fields. Okay, there's a structure to it so that they can be stored efficiently and then retrieved by on-demand basis. Okay, and then of course you can talk about the characteristic of the data. It can be a number, quantitative, right? You can represent it as a meaningful number, or it could be qualitative, which is basically like talking about some non-measurable aspect of the data. Okay, so data need not be measurable all the time. Even non-measurable data can be useful. Okay, like your hair color, your eye color, okay, the condition of your teeth, right? Yeah. So all those are qualitative data. A collection of records, yes, it can be when you have a collection of records like patient records and everything. Those constitute particular data. Information from experiments, yes, is similar to collection of records, right? You organize them to records. And finally, we have statistics collected for analysis and reference. Okay, so like for example, we have the census that's being done now, right? That's called official statistics. So basically, those kind of statistics are useful to policymakers, right? So just out of curiosity, so here it says collected for analysis and reference, right? So this will help the policymakers. Like for example, if they know that the population is aging, right? Hence is projected to be aging, then they might actually want to maybe allocate more funding to train for when they want to train doctors for specialty, right? They might actually want to train them for specialties that are related to aging, okay? And they might actually want to build more facilities for older people or things like that, right? So those kind of statistics actually need to be there. Otherwise, the policymakers have no idea how to allocate funding, okay? So yes, so this idea of asking different perspectives from you is so that I can have all these keywords and then I can build a story around it. All right, and I can build a story around it because this word itself has so many aspects to it. Right? Okay, so by the way, are you all involved in the? Any one of you registered for the e-census thing?
I think it's actually sent to every house, right?
Not every house. Some of us actually have to go online and register. If you have the code, then yes, you. But otherwise, you have to register, and then they will send you a code. Like after I don't know 1 week or 2 weeks. So it's actually a good opportunity to observe what kind of statistics is collected by the Department of Statistics Malaysia. Okay, it's very interesting. So if you can, I think you can still do that. You can still do e-census because I think the response rate is too low. So they extended it to December. So it would be interesting to do something like that. Because also now because of the COVID, right? So it's very difficult to do house visits. And house visits are very challenging to conduct in a current urban scenario because a lot of people stay in condos, right? And actually trying to interview people in condos is actually very difficult because of all this privacy thing, and some people don't want to be interviewed and all that. So it's really challenging. That's why they come up with this e-census thing. Okay, much harder to do than previously where people mostly stayed in residential areas, low density ones. So they just visit you. Okay. All right. Okay. So we have a good view of what data is, and now I want to maybe briefly talk about the data types. Okay, I want to look at the characteristic of the data. So we have the data type. Okay, let me clear my drawings. All right. So you have data types. And we have two main types, the numerical and categorical, right? So numerical data basically, I think is clear to everyone, right? It's just basically some data that you can actually assign a meaningful number, like a measurement using some instruments, okay? And numerical data sometimes is divided into two types. One is called the ratio type, the other is the interval. Like the example that I gave there would be, what is that?
Temperature and
length.
length.
Yep. Okay. Can you give me some other examples? So ratio would be something where the zero actually has a natural meaning, right? But interval, the zero does not actually have meaning. Any examples from you? Give me some examples.
Our score pH values.
Sorry, for which type?
Interval.
Interval for what variable?
The pH value.
pH value. Okay. So pH of 0, what does it mean? Yeah, meaning?
I don't think so.
Actually, pH is a measure of acidity, right?
Yeah.
So I think
SZ7
pH
is acidic. Yeah.
defined as the log base 10 of the concentration of the hydrogen ion. So I see I still know my chemistry.
Okay.
I still know it after so many years. Okay, so if you get I think here if your concentration is, let's say the neutral is 10 to the power of 7, I think. So you have a pH of 7 is neutral, right?
Yeah.
So I don't know, like this is a concentration of the hydrogen ion. Was it the negative of the? Okay, I think it's a negative, right? Is it a negative? Is it something like this?
I
Because okay, let me see. Is it something like this? And this is in like 10 to the power of minus, something like that.
yes, it's possible. I think because it's negative and yeah,
I think the negative will cancel that.
cancel that.
Because I remember that if it's very acidic, the hydrogen ions are concentrated. So something like that. But anyway, this seems to be requiring quite a lot of domain knowledge. So, and I don't know, it's very rusty for me. So maybe we can try some other examples. Anyway, you can look up about this pH thing. Anyone?
Yeah, there's message in the chat. So it will be age from Ziyun and grades from Emmy.
Grades corresponding to different. Okay, so H can be here, all right. Grades corresponding to different fractions. What do you mean, Amy? Are you talking about interval data? Because grade usually is like ABC, right? And that itself is actually like qualitative data. Ratio, time taken, yeah, okay. Interval, CGPA. Okay, so you can actually use CGPA as interval data. Over here, there are a lot of examples, right? Like the mass, okay. All right, okay, and so on, right? So I think you have, I think most of the variables that we encounter in data mining would be of the ratio type. There will be quite a lot of these things. So although like if you work with the environmental data, of course, you're going to come across temperature, okay? All right, okay, then we have categorical data, right? Which is basically something that is just qualitative, okay? But sometimes they can be given some meaningful numbers. So maybe, for example, you will have we call like examples. It could a particular class is ordinal, the other is nominal. Nominal means basically is totally qualitative. Okay. Like for example, give me some examples of nominal kind of data besides those that you see in the lecture notes. Region, okay. Region may be country, okay, the country, region, right? So these are nominal. Gender, okay, sure.
Race.
Yeah. Right, and basically anything that's descriptive, right? Like straight, curved, those are also nominal. Yeah. Language spoken, that's also nominal. Okay, so this is actually quite common, yeah, this kind of data. Now, how about ordinal data? Now, ordinal data, I give you an example of when you have ordinal data, right? It's basically it's a categorical data. Like for example, in sentiments, right? You can have strongly agree, strongly disagree, then you have disagree. So like these are actually like descriptions, right? But it is possible to actually assign a scale to it. 1, 2, 3, 4, 5. And then you treat them as quantitative, and then you proceed to use quantitative methods to analyze them. So these are what we call ordinal data. So ordinal data are somehow what we call, they are actually semi-quantitative. Okay, in some sense, the number means something, but they also cannot be taken very seriously. Okay, like they are okay if you compare between similar things that are at the same ordinal scale. For example, let's say you have a questionnaire, right? You do a survey. Surveys are very common. You have the ordinal data, okay? Like if you later you do the cost assessment, okay, using what's that? The cost assessment tool is called I can't remember what is it called for this for the courses in UM. There's an assessment tool. Like you can grade you can kind of like assign a Likert score to yeah, C-test, yeah, correct. That's an example of ordinal data. Okay, of course you can compare the average score, okay, of all the items between lecturers, okay, so that you have some idea whether certain lecturers are perceived to be doing a good job or a poor job of teaching. I use the word perceive because what the students perceive may not be what is in their interest. Okay, so although you might have, like, let's say 2 lecturers, one has a higher C-test by maybe 2 points, okay, than the other one. It doesn't mean that the other lecturer that has a high point is actually a better teacher. Okay, it's because it's a perception, right? I mean, like if a lecturer likes to give easy assignments and everybody gets an A, so of course, you know, this kind of lecturer are popular, so they will get a high C-test score, right? Whereas a lecturer that is a little bit, who wants the students to learn a lot of things, but so they give a lot of assignments, maybe a little bit more tougher, the students don't like him, right? Because they make them, the lecturer makes them suffer. So you get a low C-test score, right? So again, these are what we call observational data, right? Because there's no way, and therefore when you see C-test scores, you have to think about potential factors that could actually explain the differences. Okay, right? All right. So that completes the section on the data types, right? They're fairly easy, and so I think okay. So I think that's all we will talk about for this week. It's about okay. So because to talk further will actually take more than half an hour. So you have unusual data that we will talk about next week, yeah, until all the way until the example in figure 3.4.1. Okay. Okay, so are there any questions that you would like to ask? Maybe certain points to clarify in the notes.
Just wonder for the like our test or assignment, how is it looks like? I mean, it's like one assignment, one test, or it's like two assignments, something like that.
All the questions are hands-on. Okay, so okay, so I haven't talked about. Okay, maybe it's a good time to talk about the evaluation. For that, you have to go to in Spectrum. You can check the course pro forma and also the teaching schedule, right? Let me maybe just go to. Okay, let me just try it. Let's go to Spectrum. Okay, so can you see the course information for current semester?
Yes.
Okay, so if you, yeah, so if you scroll down, so these are just some formalities. Again, the main reference, these are some books that you can actually read, but my notes are based a lot on my own experience. And of course, it's integrated with some material from these things, okay? So, okay, you can see here, there are two assignments. Okay, and then there's a final
Yep.
final examination, FE1. All right,
Okay.
so the assignments, I think probably one of them will be a group assignment, and the other one is kind of like a self-assignment, okay? That would involve working with a particular data set and then using data mining methods to generate, to discover patterns and then maybe interpret the results, all right? For the final examination FE1, that's 50%. This one would be in the I think it's either week 15 or 16.
Oh, okay. Yeah, we got that information on the
Yeah.
UM website. Yes.
15
On
or
this-
16, and it will be in the form of some, I think it's 24 hours.
Yes, it's on the
Yeah. So
4th to 5th February.
yeah. So basically, there will be maybe some theory questions, and then some theory questions, and maybe then some problem-solving questions. Like you are given a data set, and then you have to work with that data set by using R, and then generate some reasonable results. Okay. So it's all take-home test, 24 hours. All right. So you can actually refer to, it's actually open book as well. So you can actually refer to the notes and whatever kinds of computer codes that are available. Yeah.
For the assignment 1 or assignment 2, the data set is a given data set, or actually we have to find our own data set?
Given data set.
Oh, okay.
There are actually a lot of very high quality data sets now that that you can actually look at from different perspectives and ask different kinds of questions. So, for the consulting course, maybe slightly different. But this one, we will tend to use data with certain kinds of structures. Okay.
Yep.
So let's switch back to the whiteboard. Okay. Right. So any other questions?
No.
No, here.
No. If you read the notes towards the end, I did mention something about circular data. Have you come across this before? It's a kind of numeric data, but it is somewhat different because like if you measure weight, right, you could actually put them on one line, right? So you can 10, 20, 30, and so on. It's in what we call a Euclidean space. Okay. In fact, you could have like n-dimensional Euclidean space, right? Whereby your measurements are basically just in one direction here, one direction here, one direction here. Like for example, if you measure multiple things, like if you measure your height, your height, and then what else? Your
Weight, height,
maybe your
temperature.
okay, you can measure temperature. Several things, right? Several things that you can think about. They like if you measure 5 things, they reside in a 5-dimensional space.
Yes.
But still, that space is what we consider a Euclidean space, right? It'll be something like this. Okay, and Euclidean spaces are very easy to work with. You can basically, the distances in your Euclidean space is basically just the
square root of the square plus.
You basically based on Pythagoras theorem, right?
Yep.
But in other kinds of space, like non-Euclidean space, then the concept of a distance will be different. Like for example, the distance from one point to another point on planet Earth, right? If it's far enough, it's actually non-Euclidean. In fact, it's actually non-Euclidean, but if it's actually very close to each other, the Euclidean distance will actually be a good approximation. But otherwise, it's actually a curved space, right?
Place, yes.
Yeah. So, so you have circular data is another kind of numeric data that you might actually encounter. Like for example, the direction of birds flying, right? So you have a direction here. So if you let a bird fly, right, the bird might go this direction. It may actually go this direction, this direction, right? So you can actually measure the angle, right? Here maybe 30 degrees. This one you measure an angle from some particular reference point. So this may be another angle, let's say 120 and so on, right? This is a kind of data. Once you have this kind of circular data is also called angular data. Its analysis, right, has to be treated with special methods. For example, if you measure something like 0 degrees and 360 degrees, these are actually the same, right?
Yes.
If you measure something here, with respect to here, this is 0 degrees. 360 degrees is basically you just turn like this, right?
Yep.
Okay. And basically, if you have data that's like this, it's actually the same. But if you are not aware, you use a Euclidean distance, you will think that they are very far apart from each other. They are not like this, but they are kind of like from one end they twist, it turns back to itself. So this is probably the only type, the kind of numeric data that you have to be very careful with. Sometimes you might actually get this kind of circular data, and then you will have to consult some books that specially treat this type of data. Like for example, how to do transformations to linearize it. Okay, there are some techniques to do that. Okay, just to let you be aware of it. Because the naive data scientists may actually just treat this as in the Euclidean space and then embarrass himself, right? That explains to you why when you do data mining, right, you have to pay some attention to the variable that you're working with. Try to find out something about its signs, and not just play with it. Don't just directly just play with the numbers, okay? Because the numbers have a particular context with respect to the nature of the variable, okay?
Okay.
Right, okay. So I think that's all I want to talk about for this week. And we'll see you next week, okay?
Okay. Thank you, Dr. Kang.
All right. Please check Spectrum for learning materials, yeah? For those, so I just uploaded the self-learning material for R. There's actually a zip file with some self-learning material that I used for a different course some years ago. You can actually use that to practice. Yeah, just go through it's actually self-explanatory, so you can use it for self-study. For those few students who mentioned that they Yun, Farah, Tianyi, Mankit,
yes,
Yu Jing, and Ruby. Yeah, so you can make use of that material, okay, for your self-learning. Okay.
Okay.
All right. Okay. So with that, I end this today's lecture. All right.
Okay.
So have an enjoy the rest of your evening.